Today I am going to discuss enzymatic reaction kinetics. Now, what is the importance of the enzymatic reaction kinetics? Because if you look at that biological system, I told you that mostly the reaction takes place in presence of biomolecules, and these biomolecules may be active, may be inactive material. So, but you know that we are going to deal with mostly two type of materials. One is living cell and non-living components. And living cells, they have the unique characteristics because they have the properties of reproduction. They are very sensitive to environment. Every living cell produces some kind of waste product, and overall they are very sensitive to the environment, and they have the acclimatization property. Whereas the enzymatic reactions, enzymes are very specific. One enzyme is very specific to one substrate, because one enzyme usually that they does not participate in different reactions. As for example, glucose isomerase acts on glucose and convert glucose to fructose. And if you look at the microbial system, we have metabolic pathways, and each metabolic pathways, if each steps, we require one particular enzyme. So we can consider the microbial system as a multi-enzyme system. So to understand the microbial system, first we should understand the enzymatic system. So that is why I have taken this into account, the enzymatic reaction kinetics. Now question comes, how this enzymatic reaction differ from the microbial fermentation process. Enzymes are, as I told you, very specific to the substrate, required particular pH and temperature and specific substrate to be needed. But microbial fermentation process, not that much substrate specific for the microbial growth. As for example, I can tell you, glucose can produce ethanol, it can produce acetic acid, it can produce citric acid, it can produce different type of product it can produce. But it required pH and temperature would be optimum range, because every living system also they are very sensitive. I told you they are very sensitive to the environment, so temperature and pH plays very crucial role. And overall they required, I told you also that it required carbon source, nitrogen source, minerals and vitamins. Carbon they mostly required for the growth of the cells, also a part goes for the source of energy, and one part goes for the product formation. But nitrogen mostly used for the growth of the cells. Minerals and vitamin they mostly use for carrying out as a cofactor in the different enzymatic reactions. Now, if you look at the enzymes basically they are protein molecule. Not necessarily they are protein molecule. If you enzymes can be synthetically prepared, but most enzymes they are protein in nature, and they have globular structure, and globular structure is kind of folded structure, and during this folding is due to the hydrogen bonding between NH2 and COOH the functional group with the R group of the different amino acids, and during this folding they expose one side, that is one particular side which is very specific with the configuration of a particular substrate, and that is why we call that protein with active site we call it enzymes. Protein without active site we call it inactive enzyme. So here I want to point out that enzymes are usually the protein with a high molecular weight which acts as a catalyst, and catalyst, as you know, catalyst main purpose of the catalyst is to reduce the activation energy and to accelerate the reaction. Enzymes lower the activation energy of the reaction catalyzed by binding the substrate and forming enzyme substrate complex. Enzyme do not affect the free energy change or equilibrium constant. An enzyme catalyzed reaction of substrate to product can be written as like this. This is a very general form we can write like this. Now this is how it is reduced. This is the uncatalyzed process and this is catalyzed. So whatever activation energy that is required, that will be reduced, because you see the how, and that is how the rate of reaction is accelerated. Another thing is that after the reaction is over, the enzyme remain unaltered, because that is another things that we have with the catalyst. Now this enzymatic reaction usually explained by Michaelis-Menten. There is a very famous equation they propose. Michaelis-Menten, they propose the equation between V by S on the basis of the correlation between V by S as given here. It is like this. This is the correlation that we have, and what is the equation they propose? V equal to V max S Km plus S, where V is the velocity of reaction. Velocity of reaction I can express as minus ds by dt, rate of substrate degradation, and this is the substrate concentration, and V max is the maximum velocity of reaction. This is V max, and Km is the Michaelis-Menten constant. So this is the equation that we have, and Michaelis-Menten, they propose this equation on the basis of this correlation. The question comes, how Michaelis-Menten proposed this equation, because if you look at, if S tends to 0, then what is happening? It tends to 0 here. Then if S tends to 0, I can write V equal to V max Km into S. Tends to 0 doesn't mean it is 0, it is close to 0. So I can ignore as compared to this one. So I can write, now this is constant, am I right? And if this is constant, this is 1. So we this is with first order reaction. First order reaction. So at low substrate concentration, it follows the first order reaction. Now when S is infinity, then what will happen? It comes here, it is infinity. Then your reaction will be plateau, it is almost constant. So when S is very high, I can ignore Km, and if I ignore Km, then what I can write? V tends to V max, or I can write this is equal to constant into S to the power 0. S to the power 0 means it follows the zero order kinetics. So at a high concentration, it follows the zero order kinetics. Okay. Now another thing that we have, the Vmax is proportional to the free enzyme concentration. So this is equal to, so that is why the Vmax will be equal to what? Vmax will be equal to K into E0. That is the, so three assumptions we have for this Michaelis-Menten. On the basis of that, they propose this equation. Now later on, because now another thing we have written, the Km here, Km is a very interesting. Km can be at V, when V equal to Vmax by 2, then Km will be equal to S. That is the substrate concentration. Now couple of things we have that I have, what I told, it is written here. At low substrate concentration, it follows the first order kinetics. At the high substrate concentration, it follows the zero order kinetics, and maximum velocity of reaction is proportional to the free enzyme concentration. And what is the maximum free enzyme concentration? What is the initial enzyme content? Initially we have whatever enzyme, that is the maximum enzyme concentration. So it is proportional to that. Now here in the figure it is explained like this. Now later on, because two scientists, one this Briggs and Helden, they justify the Michaelis-Menten equation on the basis of some kinetics. What is the kinetics they have saying? That I told you protein, that enzymes, they have the active site. Now your substrate, they will sit at the active site, and when they try to sit at the active site, this is some substrate can sit properly, some substrate cannot sit properly. So that is why we consider this sitting phenomena as a reversible reaction. So they are saying here your enzyme plus substrate is form the ES complex, and this is reversible. But something from ES complex, something goes back to the original form. But whatever enzyme substrate complex formation take place, that gives the enzymes and products. So I can write like the equation format E plus S, ES plus E plus P. Now if you look at this is the rate of degradation of substrate can be how we can write by K1 into S E into S into E minus K1 ES, because it is going back. This is reversible reaction. So so it is like this, and the rate of formation of ES can be written like this, that that we have this is the rate of formation, then it is going back this way and degraded this way. It forms the product this way. So it is coming like this. Now when they assume one quasi steady state condition. Now quasi steady state condition is very interesting. Here we can see that if we plot S by S0 value, what is S? Substrate concentration at time t. S0 is the initial substrate concentration. Now if S by S0 value is minimum, then the profile will be like this. And but as the E0 by S0 value increases, it is deviating like this. It is not of this pattern. Now what Briggs and Helden, they point out that this quasi state, what is steady state? I told you steady state condition. What is that? When there is a rate of forward reaction equal to rate of backward reaction, and that is possible when you have E0 by S0 value is 0.1, because but it is not that quasi steady state condition means tends to steady state, not exactly steady state, but approaching towards the steady state. So this is the thing that we have. Now here that E0 is at any point of time the total enzyme concentration equal to the free enzyme concentration plus bound enzyme concentration. Now if we rewrite this equation, the equation 4 and 5, it will come in this form, and finally we have ES equal to this. Then we have velocity of reaction equal to this. If we put, we can analyze and we can get this equation, and finally we can write this equation in this format: V equal to Vmax S Km plus S, which is nothing but Michaelis-Menten equation. But it is possible when K2 into E0 equal to Vmax and K2 plus K minus 1 by K1 equal to Km. So this is constant and this is also constant. E0 is constant, K2 also constant. Now question comes, other point I want to point out here. If you look at V equal to Vmax S Km plus S. Now what is the significance of the value of Km? Km significance is that Km indicates the affinity of substrate towards the enzyme. If Km value is very high, indicate that you required more substrate to get a desired amount of product. But if Km value is low, it indicates that you required less amount of substrate to get the desired amount of product. So this is the significance of the value of Km. And Vmax is, if the rate Vmax is high, that your velocity of reaction will be high. So what is the desirable thing is that Vmax should be, for a particular enzyme, Vmax should be as high as possible and Km should be as low as possible, and this indicates the kinetic constant of the enzymatic reaction. Now question comes, how this constant can be determined, and what will be the unit of Km? Km will be same as the substrate concentration, because Km plus substrate, so whatever unit that we have for the substrate, same unit we should use for the Km. Now three different plots we can use to determine the value of kinetic constant Km and Vmax. One is Lineweaver-Buck plot, another Adie-Hofstee plot, another is Hens and Wolf plot. So Lineweaver-Buck plot is nothing but it is the inverse relationship. You see that V equal to Vmax is Km plus S, and if you do the inverse 1 by V, then what we will get, that is Km plus S divided by Vmax S, and 1 by V equal to 1 by Km plus Vmax 1 by S 1 by Vmax. Now it is very simple. If you write 1 by V equal to Km Vmax 1 by S plus 1 by Vmax, and then if we plot 1 by V versus 1 by S, then we will get a straight line, because this is a straight line equation. Slope will give you the value of Km by Vmax, and intercept will give you the value of 1 by Vmax. Okay. So this is how we can find out the, now once we have this Vmax value, we can put here and we can find out the value of Km. So we can easily determine the Vmax and Km value of any enzymes. This is how it can be done. Now I can show you here that this slope is Km by Vmax and intercept is 1 by Vmax, and here the intercept of the x axis, here what will happen, 1 by V equal to 0, and if you put 1 by V equal to 0, then you will find 1 by Km is minus 1 by Km is equal to 1 by S. So that that this is equal to that. So you can, from the intercept also, you can easily find out the value of Km. Now this is Adie-Hofstee plot. Adie-Hofstee plot is like this. This is the same equation, and we ultimately come up this. This is V equal to Vmax Km V by S. Now if you plot a V by S, then you will negative. If you go back, that it is negative slope. Am I right? This is negative slope. So you will get a negative slope here. And this intercept, the interesting thing is that here here the this value is what? This value is Vmax. V by S, this is the Vmax, and slope will be the value of Km. So we can directly find out the value of Vmax and Km. The Km directly you can find out from the slope here, and from the intercept you can find out the Vmax value. Another plot we can have, what you call Hens and Wolf plot. This is the S by V 1 by Vmax S. So it is also similar to your straight line equation. You see this is constant and this is also constant, and this is the variables and the S is the variables. Now if you plot S by V versus S, then intercept will be Km by Vmax and slope will be 1 by Vmax. So Vmax value you put it here, you can find out the Km value. So any of this plot can be used for finding out the kinetic constant of a enzymatic reaction. Now this problem, that let us have a problem how we can really solve this problem. From a series of batch run with a constant enzyme concentration, the following initial rate data were obtained as a function of initial substrate concentration. So, as the substrate concentration, initial substrate concentration increases, your rate we observe at the different. To evaluate the Michaelis-Menten the kinetic parameters. Now, this is this is the Lineweaver equation that we have already derived. So, if you look at this equation, this table, and from this table this is S, this is V. So, we can write 1 by S by 1 by V value. So, 1 by S by 1 by V value we can write that, and then we can plot. We can plot 1 by V versus 1 by S, and we will get a straight line, and from the slope we will get the Km by V max, and intercept will give you the value of V max. And then we can calculate, we find the V max equal to 0.54 millimoles per liter per minute, and Km equal to 1.75 millimoles per liter. So, this is how we can now, a couple of interesting things. We have enzymes that enzymes are very sensitive to the temperature also. As you increase the temperature, what will happen that I told you that enzymes are basically the protein molecule, and they have the globular structure, and this globular structure, the folding nature of this the protein, and this folding is due to the hydrogen bonding. Now, when we increase the temperature, that we give some kind of heat energy, and hydrogen bond has some energy. It is usually the 3 to 7 the kilocals per mole. Now, if you increase this heat, then what will happen? Slowly the hydrogen bond will be loosened, and when a time will come when it will be totally folded structure will be unfolded. When it unfolded, then enzyme will lose its activity. Now, we know that we have a correlation, that what we call Arrhenius equation. That K equal to A e to the power minus E A by R T. Am I right? Now, if we plot, if we take log ln K, then ln A minus E A by R T. Now, if you plot here the semi-log paper ln K by 1 by T, so you will get a slope like this. And then it will fall down like this. Now, here I want to tell you something, that because I told you the enzymes, they are catalyst, and they are basically biocatalyst, and we have several reactions in the chemical engineering, which is carried out by also different catalysts like platinum, palladium, nickel. They act as a catalyst. Now, how those this catalytic reaction differ from enzymatic reaction? Now, this enzymatic reaction, as you increase the temperature, when your protein molecules unfold, your this fold will be very sharp, because you know that because when it unfolds, it is the irreversible phenomena. It is not a reversible phenomena. But in case of inorganic catalyst, this even you increase the temperature. This is the increase of temperature. 1 by T decreases means T increases. So, as you increase the temperature, then slowly activity of the catalyst will go down, and it decreases like this. This is how it differs from enzymatic reaction and the chemical catalytic reaction. This is how they differ from it. Another very interesting thing, when we go to the market, we want to purchase the enzymes, we always concerned about the what is the stability of the enzyme. That plays very important role. Now, how you find out the stability of the enzyme? Stability of the enzymes, we determined with respect to the half-life of the enzyme. Half-life of the enzyme. Now, if the half-life of the enzyme is more, that means stability of the enzyme is more. Now, naturally, we know the proteins are very costly, and protein with active sites, we call it as enzymes. So that will be more costly because this is the active enzyme, active proteins. And so question comes that stability of the enzymes, that plays very important role. And question comes how we increase the stability of the enzymes. The enzyme stability can be increased 3 different ways. One is by immobilization of the enzymes. If we suppose there is a solid matrix, and this is the solid matrix, and you immobilize the enzyme on the solid matrix, or you have membrane. Inside the membrane, if you store your enzyme, so you can, there are different techniques of immobilization that I shall discuss, because immobilization technique has several advantages and that is used by the industries. So different way this can be, it can be, the stability can be improved. Second approach is that enzyme with active sites, suppose this is the active sites, and if we have some kind of polymer of amino acid, polyalanine, we have find that it is in found just close to the active site, it gives some kind of protection to the active site. Another is the substrate analog. If you have some kind of substrate analog or some kind of presence of some kind of metal ion, we can increase the stability. I can give the example of alpha amylase. Alpha amylase enzyme in presence of calcium ion, stability of the enzyme increases to a great extent. So like this, that stability, so this plays very important role. So in conclusion of what I want to tell, that enzymes, they are globular protein, mostly they are globular protein, they have the active sites, and the enzymatic reaction can be explained with the help of Michaelis-Menten equation, and Michaelis-Menten, they propose this equation on the basis of the correlation between Vmax and S, but later on the Briggs and Helden, they justified the Michaelis-Menten equation with the help of reaction kinetics, but they say that substrate that sits at the active sites, and this is the reversible phenomena, something sit properly, something cannot be sitting properly, that lose that slip out. And but whatever enzyme substrate they sit properly, they give the product, that is irreversible reaction. On the basis that this justifies the Michaelis-Menten equation, and then we have seen that that enzymes, they are very sensitive to the temperature. At the high temperature, protein undergo the folding structure will be unfolded, then whole activity will be lost, and the stability of the enzyme plays very important role, and this is determined from the half-life of the enzyme. Thank you very much.